Swayam Prabha. Digital India. Educated India.
In this lecture, we will discuss some coarse-grained MD simulations. Before we talk about coarse-grained MD simulations, let us talk about what we know about MD simulation in first place. This is something we have been discussing for quite some time now, but just to recollect some of the important features of MD simulations, we look at how it works. For any given system, single component or multi-component, we have to look at the position and momenta of each of the species, and then we have to define a Hamiltonian, which is basically defining the total energy of the system, which includes intermolecular interactions and kinetic energy of the system. So, once we have specified this Hamiltonian, then we can derive a set of equations of motion by which the system basically evolves in time. And these equations of motion can be derived either via Lagrangian dynamics or via Hamiltonian mechanics, and both are equivalent. Once we have these equations, we realize that we cannot solve them analytically because the interactions are pairwise additive, and we have to solve them via numerical techniques. And we also discussed various types of numerical techniques where we take the system at specified initial condition, and then we take a small time step delta t, and then we integrate the equation of motion numerically. And we looked at various kinds of algorithm like leapfrog, Verlet, velocity Verlet, predictor corrector methods, etc. So, we can choose any one of this method to advance the system in time. Now, we also have to recognize that the way of doing this MD simulation or the equation of motions that we have in the system, they have certain properties. For instance, the total energy of the system is conserved, and this basically implies that the system is time reversible, and the linear momentum also is conserved as per the equation of motion. So, that basically says that if I translate the system in space, the property that we measure should not depend. Similarly, the angular momentum is also conserved, meaning that the property that we measure is basically symmetric about rotation of the system itself. So, these are characteristic of a classical mechanical system following Hamiltonian or Lagrangian equation of motion. However, we noted that in MD simulation, we have to deal with a certain finite number of particles, thousands, 10,000, 1 lakh, etc. And then to manage such a small system size, we have included certain concepts, namely periodic boundary conditions, potential cutoff, etc. Because of this implication of this periodic boundary conditions, we also showed that the angular momentum will not be conserved. In principle, the equation of motions conserve the angular momentum, but not the MD simulation as we do it. So, these are some of the key ideas one will have to remember when we think about MD simulation. Now, when we go to coarse-grained simulations, we will have to see that which of these properties are compromised when you go from a pure MD simulation to a coarse-grained MD simulations. Now, when we talk about coarse-grained or multi-scale simulations, so there are two levels we can think about. One is in modeling the system itself, we can do a coarse graining. For example, you can group bunch of atoms together and then make a super atom, and then that's one way of coarse graining the system. So, the coarse graining can happen at the description of the model itself, going from atomistic to superatomic to some other types. There is other class of methods where the dynamics itself, the equation of motion itself is coarse grained. So, there are two levels. We have already talked about the first level where the molecules are coarse grained in certain description. Then the other way is to look at the coarse graining of the equation of motion itself. So, we are going to talk about the second aspect. So, now where is the need for such a coarse grained simulations? So, typically what happens is that in a system, when we try to simulate, we see that there are certain types of motion which are very fast, rapid, and there are others which are very slow and sluggish. And then if you go about numerically solving such a system, your choice of the time step will be limited by the fast motions, which means you have to take a very, very small time step delta t so that you can resolve all the fast dynamics. And this will unnecessarily increase the computation time, because the property that you need to measure from the slow motions will have to be will be observed only in a very long time behavior. So, you are going to take a very small time step, so you can resolve the fast motions, at the same time conduct the simulation for a very long time, so that the properties coming from both fast and slow motions can be averaged. In many cases, we see that even the fast motions may not be very important. For instance, if you look at a water molecule, we may be interested in the collective motion of the water molecules to get some bulk properties. So, in this sense, we may not be so much interested in the bond vibrations and angle bending and angle stretching. So, we could treat such unnecessary variables as a constraint, rigid constraints, and that is what led us to define rigid body dynamics or rigid constraints. This is something we already looked at in constrained MD simulations. But this approach is not always going to work, because there are certain situations where we have to completely ignore certain components of the system because they are not relevant, they are not useful for the kind of question that we would like to ask. The time scale, length scale of the question that we pose are so different that many of these fast motions are unnecessary to keep in the MD simulations. So, we would like to basically come up with a way where we can actually integrate out all the fast motions, think about them as some sort of a continuum or mean field description, and then keep only the degrees of freedom of which we want to study. An example could be, think about a protein molecule in water or a polymer molecule in a water system. In these cases, if you want to simulate a protein solution or polymer solution, you will see for every one macromolecule, you will have to simulate large number of water molecules corresponding to an experimental conditions. So, much of the simulation time will be spent on simulating water, whereas you are actually going to look at the properties of the protein or the polymer in the system. So, in such a case, we can actually think about the solvent being in the background and try to describe it implicitly and focus on attention to the actual system at study, which is the protein or the polymer. So, so this is again kind of way of thinking about how to model the system. What are the components that are important? What are the effects that are important that we want to bring out from the simulations? So, you have to make a judgment about which one to keep, which one to average out. So, when we try to do all these things with this as a motivation, we will see that we will go from Newtonian mechanics to another mechanics called Langevin equation. So, the context of this lecture is to show how to do this Langevin dynamics for a coarse-grained description. So, now the conventional dynamics that we have been doing in MD follows Newton's law of motion, which can be derived from Lagrangian mechanics, where the rate of change of momentum is given by the force, and this force comes from the intermolecular forces, inter or intramolecular forces. So, here we write this equation for every species in the system, solvent, solute, etc. But now, if you think about having this solvent as a background as implicit, and you do not have to worry about the solvent's degrees of freedom, but then bring the effect of this solvent into some other form into the dynamics. So, that basically brings us to what is known as the Langevin equation. So, if you look at structurally, we have a very similarity between Langevin dynamics and Newtonian mechanics, where the rate of change of momentum of a species is given by a sum of three forces. The one in the middle is the conservative force, which we already know comes from the intermolecular force. In addition, the effect of solvent is encoded in two additional forces. One is the frictional force, the other one is the random force. So, now if you think about this protein molecule moving in a solvent, this protein molecule will experience a lot of incessant collisions by the solvent molecules, okay, and this collision could be considered as a random process. So, the net effect of the solvent bombarding on the protein molecule could be described by a set of random forces. And as the protein moves in the solvent, it also experiences a drag because there is a solvent around it with some finite viscosity. So, this drag resistance is coming from this frictional force. So, we are able to basically map the effect of solvent on the solute via two additional forces, namely random force and the frictional force. And this friction coefficient or the friction constant eta here can be shown to be related to the diffusivity of the system through Einstein's relations. So, when you try to advance the system's trajectory through Langevin dynamics, what we are basically simulating is we are simulating a free Brownian particle, especially when f is equal to 0. Whereas, when f is equal to finite, we are basically simulating an interacting Brownian particle in the system. So, this is the context with which an equation of motion itself is coarse grained to bring about the effect of solvent in the system. So, now in this Langevin dynamics, we are going to keep only the degrees of freedom of the solute. In this case, it could be a protein or a particle or a polymer molecule, and we do not worry about the degrees of freedoms of the solvent, and they basically influence the dynamics via the random force and friction force. So, now what I wrote in the last slide, that is this equation, is basically written in a vectorial form. Okay. So, we have to recognize this capital P dot here is basically the rate of change of momentum for each particle with the 3 components. So, now if you write in component form, you can write into a set of scalar quantities. The Pi alpha here is basically the ith particle's momentum's alpha component, where alpha can be either x or y or z, and this I basically goes from 1 to n. That is the number of solute particles that we want to simulate. So, we have this term which is a frictional term, then we have this conservative force which comes from intermolecular forces, and this is the random force that we need to calculate. So, now one of the characteristic of this Langevin dynamics equation is that if you look at the momentum autocorrelation, it basically exponentially decays with a proportionality constant given by the friction coefficient eta. So, depending upon the value of eta, the momentum correlation decays exponentially. So, this is something important because later on I am going to tell you various algorithms by which we can solve the Langevin dynamics, and each of this algorithm depends on how we are going to model the momentum autocorrelation decay. So, now if you look at how we derive this Langevin equation, so there is a sound theoretical basis which you can start with your Newtonian mechanics, and then you can project out certain number of degrees of freedom which you do not want, especially the solvent degrees of freedom, and then you can derive the set of equations, and a lot of assumptions goes in how we derive these equations. But I think for this particular course, we do not want to go to the theoretical derivations which is besides the scope of this course. We will look at the form of the equations and how we go about using these equations in advancing the system. So, now we have got a set of equations that says how the momentum and particle position changes in time, which is basically simulating a Brownian like motion of the solute in the background solvent, which is implicit. Now, we need to know how to discretize these equations and then how we implement the algorithms. So, now when we go about deriving a algorithm, there are many algorithms. The one I am going to talk about here is known as Ermak's algorithm, and the basic assumption in this algorithm is that these equations, especially the momentum equation here, is basically integrated over a small time step delta t, with an assumption that over a small period of time delta t, the conservative forces Fi alpha here stays constant. Okay, so, that is the basic assumption, and as I said before, each of these algorithms will make certain assumptions, and because of that, the actual equations will take a slightly different form. But in this Ermak's algorithm, we are making an assumption that over a small time step delta t, the conservative forces can be considered constant. And then you take this equation and then you integrate in time. Okay, and when you do that, you can write the next time step velocity using the current time step velocity and the current acceleration. This acceleration comes from the force, and then there is an additional contribution to the velocity via the random contribution. And similarly, if you integrate the for the particles, the particle position at t plus delta t is given by the current position plus some coefficients times the current velocity, and then another term that relates to the acceleration, and finally there is also an additional term that comes via the random contributions. So, if you look at all these equations, there are many numerical coefficients C0, C1, C2, etc., and all of them can be shown to be a function of the friction coefficient. For instance, the C0 here that you see here is basically equal to exponential of minus eta delta t, and this coefficient C1 here and here, they are basically related to C0 itself as 1 minus C0 times eta delta t inverse. And similarly, this C2 here is defined in terms of 1 minus C1. So, now these are all written, and then if you take eta t to be very, very small, you can even expand this into series and then take only the leading order. So, now once when you do the simulations, what you generally do is you specify a particular time step in the simulations, and the friction coefficient also is something that is defined because we know the solvent viscosity and temperature. So, we can calculate what is the friction coefficient. So, once we have a numerical values of this eta times delta t, then all these coefficients C0, C1, C2, everything can be calculated. Now, the only thing that are unknown are these random contributions to the velocity and the force. In fact, you will see that if you look at the actual definition of these variables, this would be some time integration of this random force, okay, when we do this time integral. But again, I am skipping that particular form of equations, that is not relevant here. Now, we will just worry about how to get the random contribution to the velocity and random contribution to the position. So, this is our discretized equation of motion for Langevin dynamics, and it turns out that this two random variables are basically correlated bivariate Gaussian random variates, and again the theory is there in the background. So, what we need to know here is we have to first find out what is the variance in R and what is the variance in V, and again these are related to all the quantities that we already know, that is in terms of the friction coefficient, mass, temperature and delta t. Similarly, the variance in the velocity is also expressed in terms of mass, temperature and the friction coefficients. So, that means all these things is something you can calculate numerically for a given simulation. So, once we have this, we also get a correlation coefficient between the position and velocity. So, in this particular algorithm, we see that the random variables for the position and the momenta or the velocity are not independent, but they are correlated, okay, and the correlation coefficient is given by this. So, now the question is, at any given time step delta t, we know all the numerical coefficients C0, C1, C2, delta t also is known. We have to sample two random variables for delta v and delta r from a correlated bivariate Gaussian distribution, and the way you do that is, again, you first generate two random variables zeta 1 and zeta 2. Zeta 1 and zeta 2 are basically unit normal random variate. So, this means the mean value is 0 and variance is 1. So, this is basically simple normal random distributed random variables. So, once you have this zeta 1, zeta 2, then you can multiply zeta 1 with the standard deviation for v from here to get delta v, which will be going into this particular expression. Similarly, to get this delta r I alpha for each component, you take this eta 2 and then do this mathematical operation, and that will give you two random variables that goes in here. So, what we need to do then is, apart from calculating forces at every time step like we do in MD simulations, we have an additional process to be done where we have to draw random numbers at every time step that follows a bivariate correlated Gaussian random variables, and those numbers goes in here apart from calculating the forces and velocities, etc. Okay. So, this is the way in which the Langevin dynamics is done as per the Ermak's algorithm. So, now you can also show that this Langevin dynamics eventually will converge to a Newtonian mechanics in the limit that eta goes to 0. So, when eta goes to 0, that basically means it is like a inviscid flow. That means there is no friction, the solute does not really feel any frictional effects in the medium, and when the friction goes to 0, you will also see that the random force also goes to 0. And to see that, you look at the expression for C0, C1 and C2, and when eta goes to 0, you can expand all these terms, and then you can show that C0 will become 1, C1 also will become 1, and C2 will become 1/2. And then when you substitute all these C0, C1, C2 values in the velocity and in the positions here, you basically will recover that the Langevin dynamics basically converges to Newtonian mechanics, as if this is a Taylor series expansion of velocities and positions. And we also see that when eta goes to 0, both the random contributions also goes to 0. So this basically tells us that the deviation between the Newtonian mechanics and Langevin dynamics is dependent on how much is the friction in the system. Okay, so when you have a very viscous fluid or viscous solvent in the background, we basically move away from Newtonian mechanics to a Langevin dynamics. And whereas when this friction coefficient is tending to Langevin dynamics algorithm, there are quite a few, and they all depend on how we model the forces and whether the forces are held constant during the integration or whether they are allowed to change. For example, in one variation, when we integrate this Langevin equation of motion in time delta t, we keep this force, conservative force, as a variable in time which is linear. In the previous Ermak's algorithm, we held Fi alpha constant over delta t, but now in this another algorithm, this Fi alpha is basically allowed to change in a linear fashion in time. So when you do that, and then you can do a time integration, and you can show that the discretized equation of motion for the Langevin dynamics will have an additional components where the acceleration at the next time step is also involved. And then when eta goes to 0, you will see that this set of equations basically converge to our velocity Verlet algorithm that we used for MD simulations with Newtonian mechanics. So depending upon how we model the forces during a delta t time step, you can get different kinds of algorithm. But what we discussed today is the two most important algorithms that are used in Langevin dynamics. So now we can also do one more modification or approximation within the Langevin dynamics. That is, if you are wondering about a long-term configurational dynamics are interesting, then we can even leave out all the momentum variables in the system. Okay, so what I mean by that? So if you look at the Langevin dynamics, we solve for position and velocity at the same time. Now, if you think about this momentum correlations, it basically falls exponentially with the time step with the rate constant eta. So if you are looking at the system at a broader time scales, you can see that the velocity could be held constant over those period of time. So the momentum correlation dies out very quickly as long as you take a larger time steps. So for t or delta t larger than this inverse of this friction coefficient, we can show that this momentum correlation basically decays within the time step. So in such a case, we can leave out all the momentum variables and work with only the positions. So what this basically means is, in the Langevin equation, the sum of all the forces basically becomes 0, because if the momentum becomes constant, then the acceleration basically goes to 0. So we keep this term 0 and then solve for, so you set the sum of these forces to be equal to 0, and then this particular term will have a velocity, and then you solve for velocity from here, and you get a much more simpler expression for the dynamics. So, so here you have only two terms. One is this conservative force term, the other one is the random force term. But again, we have to recollect that the friction coefficient is given by Einstein's relation. So in this particular method, the random component is known as random velocity process, and and the correlation function between this velocity process, random velocity process, is actually given by this expression where you see this d is coming up, which is the diffusivity for two particle I and j and components alpha and beta. So the point we are trying to say here is that we can do one more approximation in Langevin dynamics where we can keep the velocities constant between time steps, and this is possible only for time scales larger than the inverse of friction coefficient. Okay. So in that case, we can leave out all the momentum variables, we just solve only for the position. So because of this, we call this as a position Langevin equation, or also known as Brownian dynamics. So, in the Brownian dynamics, we do not have any velocity explicitly there. We are going to just take this expression and solve for position at every time step. So, this is shown in terms of a discretized equation. So, you take this equation, and then you discretize this in time, and then you basically can update the particle positions as a function of time with using the current time, the current force, and the random contribution. This random contribution is again sampled from a Gaussian distribution with a mean 0 and a variance of 2d delta t. So, in this expression we do not have velocity explicitly available because we are solving only for the position. So, if you want to look at mean square displacement or any variable that depends only on the configurational degrees of freedom, then one would do a Brownian dynamics because you are not interested in any momentum based properties. So, this is another approximation one can do in the Langevin dynamics. So, now when we think about Langevin dynamics or Brownian dynamics, there are some key issues that we have to remember, and these key issues come because of the way we have formulated this theory, which makes a lot of assumptions. For example, one of the restrictive assumption is that the dynamics of the Brownian dynamics or Langevin dynamics is not very physical when you look at a very short time behavior. Okay, so this works only when you look at long time behavior. And the another important assumption that went into the derivation of Langevin dynamics is that the solvent effect on the particle is occurring through collisions, and then you ask whether the collisions are remembered by the particle or whether the collisions are independent. So, we make a very restrictive assumption in deriving those Langevin dynamics, where we think about this collisions to be a delta like function. Okay. So, now if you look at very short time scale processes, such assumption may not be valid anymore. Okay. So, that is a physical reason why Brownian dynamics does not give a physically realistic trajectory for very short times. On the other hand, if you are worried about only the long time dynamics, then this Langevin dynamics gives a correct description of the system. And we also will have to note that in this case, there is a friction and there is a random force, there is a lot of dissipation, and because of which the energy is not conserved, momentum is not conserved. In fact, only the number of particles is conserved in the Brownian dynamic simulations. And we also have to think about this effect of hydrodynamics. So, even though the solvent is imparting a random force and frictional force on the particles, but there are also other kind of interaction known as hydrodynamic interactions that occurs as the particle moves relative to each other in a viscous medium. So, Brownian dynamics do not consider this hydrodynamic effect in the system as well. So, these are some of the limitations that we have to keep in mind when we think about Brownian dynamics. So, with this I would like to summarize that in the Langevin dynamics, we basically hope to average out the solvent effects by imparting an effective random force and frictional forces, and we could use a standard discretization algorithm we used for MD simulations, which could be velocity Verlet algorithm or Verlet algorithm, with one additional correction that we also need set of random numbers along with these algorithms. And we also see that how these random numbers are generated and what is the underlying distributions. And one further correction one can make, approximation one can make in Langevin dynamics is by converting into a positional Langevin dynamics by dropping the momentum variables and only updating the particle positions in time. And that is basically brings us to the Brownian dynamics. And then we also recognize that this Brownian dynamics has several limitations in terms of not accounting the hydrodynamics interactions, not conserving the momentum, energy, and it is not time reversible, it is more of a stochastic nature. But despite all that, if you are looking at simulating a Brownian like